So as you've already seen in the web-based application we've been using to explore 2, 3, 4 trees, it's actually referred to as a type of B tree. So I want to take just a minute to talk about B trees. And one of the places where B trees really shine is in something called the block-based access. So I'm going to look at the Wikipedia definition of the B tree. Okay, so B tree is a self-balancing tree data structure. Operations are logarithmic, but what's a little bit different here is these are not binary trees, and in fact they're even typically have larger nodes than what we saw with the 2, 3, 4 tree. So this is a logarithm with a different base than what we've been seeing so far, and that can actually lead to efficiency in certain situations. So by the way, it sounds like, at least if Wikipedia is to be believed, the B and B tree what it actually means has been kind of lost to history. One of the inventors had the surname Bayer, but they were working at Boeing Research Labs, and there are several different suggestions about what the B may actually stand for. Okay, so the concept of B trees is pretty similar to what we've seen with 2, 3, 4 trees. We've got nodes that can contain multiple keys. It's just we're going to generalize it, and instead of being limited to 2 to 4 different subtrees, we'll be able to have many, many more subtrees. We could have a node that contains a particular number of keys, more than just 3. So there is a range limit. Basically, the number of keys will be between D and 2D. So you have a maximum size of node and a minimum size of node. There are some special situations where you've got a tree with fewer than D values total where you're allowed to exceed these constraints. But once you have enough data, the constraints are enforced for all nodes. Okay, so this still undergoes kind of the splitting sort of process that we've seen and the merging sort of process. It's just individual nodes contain more data. Now, that can be really valuable in certain situations where, for example, if all of the data doesn't fit in your computer's memory at the same time and you need to go and grab data off of a disk or off of a network. Typically, getting a single item of data takes a lot of time. Getting multiple contiguous items of data generally is only a little bit more time than just getting the first item. So oftentimes devices that have this feature are referred to as block devices. So a classic mechanical disk was an example of this. The mechanical disk, the actual disk would have to spin and you'd have to physically move to where the data was at. But once you got one piece of data, all of the other data was kind of immediately after it. And you got a big block of data for just a slight bit more cost than just getting the very first item that you were interested in. So B trees can really accelerate at block-based storage medium because basically they kind of allow you to get the minimum number of blocks and consequently minimize the overall amount of time. So the size of the individual node, these limits the D to 2D, it's actually typically based on the block size of a data access device like a disk. Okay, so the B tree is just kind of a generalization of what we've seen with the 2, 3, 4 trees, and there are certain situations where it has quite a bit of benefit.